Hello everyone, I'm Keshav, a PhD student working at the IIT Bombay Monash Research Academy. I'm working with Professor Basudev Biswal from IIT Bombay and Christoph Rudiger from Monash, and I predominantly work on conceptual flood inundation modeling. Jumping right into our presentation for the day. So I look at different models that can predict or map inundation across large geographical regions. And I found in literature that numerical models are consistently used. They solve the conservation of mass momentum energy equations, and they are very time taking for large regions. And if you look at, especially for high spatial resolutions, conceptual approaches aim to look at satellite imagery based mapping of inundation. And with the explosion of computational facilities, so this has been the way to go towards using artificial intelligence based techniques in mapping inundation. However, we do not have the depth or the discharge information associated with a given extent across large regions. So we actually cannot model the actual depth very consistently. And in addition, we have very high error associated with the topographic metrics associated with the digital elevation models for a region. So my project aims at developing a flood model which can consistently correct for the errors in the digital elevation models and also map inundation across large geographical regions by pre-processing extents. So inundation models generally consist of two parts, the hydrological as well as the inundation and routing model itself. So here we employ a dynamic Budikoff framework to model rainfall to runoff. We sort of model the initial losses in zone 1, losses due to ET and infiltration. And in zone 2, we actually model the continuing losses with the help of decay function, which is modeled as a function of time. The graded runoff is then subject to the catchment that is delineated with the help of DEMs. Here we characterize the catchment as a set of independent channels, and we find the relationship between the height and distance to pore point of every pixel on the independent channel and take the derivative of this relationship to model the conceptual slope. We then also have proposed a velocity updation procedure based on Manning's equation. We have modeled a Banfield velocity discharge, which is considered to be spatially constant for a given instant. And once this model assumed Banfield discharge is assigned to all the reaches, we compute the discharge at the pore point, where we have the pre-computed discharge velocity relationship. For the computed discharge, we find the updated velocity, which is then assigned to all the upstream reaches. We then iterate this process till we stabilize the velocity and we have a stable discharge computed for all the reaches. Corresponding to the discharge we obtain, we get the height above the nearest drainage value associated with this discharge, and we map the inundation within each reach contributing area. I was able to map the inundation for different flood events across Kerala, India, and Louisiana, USA. And the Kerala, India flood event was a 1 in 100-year flood event, which is pretty catastrophic. And you can see that it affected a large geographical region. So we were able to map the probability of inundation by considering an uncertainty in the Banfield depth and width values. We also tested the model for different DEMs, in the case of Aster and SRTM, at different resolutions. And we found that 90-meter DEM was able to map inundation accurately using the flooding accuracy as a metric for comparison. And in the case of Louisiana, we used the USGS-based flood maps for comparing our model results. And here we found out the flooding accuracy kept on increasing as you made the model coarser. So we had to come up with a more holistic metric which can evaluate the flood map more appropriately. And we assumed the critical success index to indicate relative performance. But even this indicator was not actually giving us a very good measure. So we had to depend on the Udens index, which actually tells us the agreement between the modeled and observed flooded and non-flooded pixels. And that gave us a very holistic measure between the flooded and non-flooded maps of inundation developed by the model as well as what is given by USGS. We feel that the model is fit to be operationally deployed, and it has a application in data scarce regions, and it can be employed over large regions at relatively high spatial resolutions for policymaking. And we feel that model can be used for disaster management as well as for insurance purposes. I look forward for collaborations, if any, and encourage questions on the same. Thank you.